Hi, ladies and gentlemen. I'm Michael Ukpe, and today we'll be talking on protein calibration curve. We are going to take some sample questions and we are going to go through it together. Given a protein standard solution labeled as Q, having a concentration of 500 mg per dl, your objective is to establish a protein calibration curve encompassing a range of 0 to 100 mg per dl. This curve serves the purpose of ascertaining concentrations of samples M, N, and P. Following the sulfur salicylic acid method for protein determination, introduce 2 ml of 3% SSA to 200 microliter of the sample, followed by 5 minutes incubation at room temperature and subsequent absorbance measurement at 420 nanometer wavelength. So now we'll look at the principle of SSA for protein determination. The sulfur salicylic acid method is a widely used technique for protein estimation. In this method, SSA causes protein coagulation by forming hydrogen bonds with protein cationic amino acids, leading to precipitation, which will result in the formation of a turbid solution. The amount of turbidity is proportional to the protein concentration. By measuring the absorbance of the solution at a specific wavelength, in this case 420 nanometer, the protein concentration can be determined. Let's begin by learning the dilution calculation required. Imagine you want a protein concentration of 100 mg per dl, but your stock solution is stronger at 500 mg per dl. We use a formula to figure out how much of the stock solution to add with water to get the right concentration. The formula is RV over O, where R is the required concentration, that is the concentration you want to prepare. V is the required volume, the total volume of what you want to prepare, and O is the original concentration, that is the concentration of the stock solution provided. Let's say you want to make a concentration of 100 mg per dl. First, we need to know how much sample to use. We'll be using 200 microliter for our sample. That is, in this case now, our required volume. When calculating, R here will be 100 mg per dl, O will be 500 mg per dl. That is the original concentration of the stock solution. V will be the total required volume I want to prepare, that is 200 microliter. The product of this calculation will give us 40 microliter. This means that 40 microliter will be taken from the stock solution. But remember, our total volume is 200 microliter. To make it up to 200 microliter, we'll do a simple math. 200 minus 40 will give us 160 microliter. This means that we will add 160 microliter of our diluent to make it up to 200 microliter. With this, we have learned that to prepare 200 microliter of 100 mg per dl from 500 mg per dl stock solution, we will prepare 40 microliter of the stock solution and add 160 microliter of the diluent, in this case, distilled water. We will repeat the same calculation for 0, 25, 50, 75, 100 mg per dl and input values in the protocol table. The protocol table shows the amount of stock solution and diluent needed to make up the required concentration. Here you add 200 microliter of sample labeled M, N, and P to labeled test tubes. Add 2 ml of SSA to all tubes and incubate for 5 minutes. For each dilution and samples, measure and record the absorbance using a spectrophotometer at 420 nanometer. In the result, you have the absorbance and the concentration in a tabular form. Write the absorbance against each concentration. Plot a graph with absorbance on the y-axis and protein concentration on the x-axis. Plot the absorbance value for the different dilutions. Fit a linear regression line through the data points. To calculate the unknown sample concentrations, there are two methods to go about this. Method 1, from the absorbance value of each unknown sample, trace a vertical line until it intersects the calibration curve. From the point where the vertical line intersects the calibration curve, trace horizontally to the y-axis to determine the corresponding concentration. Follow the same procedure for all the unknown samples, that's M, N, and P, to determine their concentrations. In method 2, we can employ the calibration curve equation, which is y equals mx plus b, where y represents absorbance, x concentration, m denotes the slope, b signifies the y-intercept. Insert the measured absorbance values of the sample m, n, and p into the equation to calculate their respective concentrations. I know it's been a mouthful. Thank you for sticking with us to the end. I hope you learned from it. See you in the next video.